Hey, this is Mr. A, and I would like to do a balanced forces problem, finding the coefficient of static friction. And this was a problem that you should have worked your way through in the lab, and we had some homework or at least some example problems on this. But it's the case where you have a block of wood on top of another block of wood, and you're going to pull that wood with some applied force. And I'm just going to make my force gauge as a little dial here. Okay. So there's a force to pull the block, but as you know, there is going to be some friction force, some friction between the two pieces of wood that's going to oppose that motion. Now, when you're finding the coefficient of static friction, you're going to pull, you're going to apply force until just before it moves. Because after it starts moving, then we're talking about kinetic friction. This question is about static friction. So make sure you're going for the right, trying to solve the right variable, because you'll get lost if you really don't understand the problem. In both situations, you are pulling on the block, but when you're trying to find static friction, the block isn't actually moving. You're going to take that measurement just before the block starts to move, and that, that's a little bit tricky, and some of the gauges will hold a maximum value, but the way we approach this mathematically is to well, first we need to draw a free body diagram so that we can see all the forces involved here. So I'm going to represent this block as a particle, and the block has mass, and so gravity is going to act on it, and there's going to be a normal force also. The block is pushing down on the plank of wood, and the plank of wood is pushing up on the block in the same amount. So our force of gravity and our normal force are both equal, because the block isn't going up or down, it's just sitting there. Now we are applying a force, and this will be my force applied. And meeting in opposition to that force is the force of friction. Okay. Now this is a balanced forces problem. So all of these forces are going to be in balance. Well, the normal force is going to be equal to the force of gravity, and the applied force is going to be equal to the friction force. Now the question is what is the coefficient of static friction? So mu s. That's what we want to know. But before we can do that, we've got to put in some values here, right? So I'm going to try to use some realistic values for the block in the lab. And if you took this block and you weighed it over on the scale, you would have found that the block of wood, the mass of the block of wood, was about, 150 grams, which I'm going to write as kilograms, because it's really important that you use standard units if you're going to use standard equations. So the scale in the lab read 150 grams, but when you write this down as your data, you need to write it as 0.150 kilograms. Okay. Is that enough to find out what we need to know? Well, the other thing that you determined experimentally was that when you pulled on the block with the force gauge read, the applied force read 0.45 newtons. And that is all we're told in order to find mu sub s. Well, because this is about a balanced forces problem, we can set some things equal to each other, and we can use some of the equations that were in the chapter. And first I want you to recall that friction force is the friction force of static friction is equal to mu sub s times the normal force. All right, so the more weight that's on this block, the greater the force that friction, the greater the friction force is going to be. The other thing you need to remember is that this normal force is calculated by the mass times the acceleration of gravity. Right? So now we can find our normal force because we know our mass and we know the acceleration of gravity. And do we know the friction force? Well, we do. Again, this is a balanced problem, so our friction force is going to be equal to our applied force. Okay, so in these problems, it's very important that you set it up properly by realizing that this is a balanced forces problem. So I know it feels like I'm kind of all scattered out through here, but I think that we have everything that we need to solve for. Okay, so first of all, I want to substitute f of a for f of f. So f of a now is equal to mu sub s, and then I want to substitute mg for f of n. Okay. Now we're still trying to find mu sub s, and this formula that we have is an improper form. But if we just divide both sides by mg, then we get the variable that we're looking for. So mu sub s then is equal to f of a over mg. Okay. And now we can plug in our experimental values. We got 0.45 newtons. And we divide that times the mass of the block, 0.150 kilograms, times acceleration of gravity, which is 10. So, if I do my math right, then I find that the coefficient of static friction for wood on wood is 0.3. It's important. I want it important to note a couple of things here. First of all, this coefficient of static friction, we are looking for the coefficient of static friction. That is a unitless value, because at this point we are dividing newtons by newtons, and so this is a unitless value. The other thing I wanted to point out is that when we multiplied by 10 here, the acceleration of gravity, which is really 9.8, but we use 10 for simplicity, that has units associated with it too, as meters per second squared. Those are standard units, so we had to use the standard units of kilograms so that these units would work out. That's why I'm going to be particular about when you mass something in the lab, that you convert it to proper units, which is usually kilograms. Okay. Well, that is that problem solved. Now you may see different versions of this problem where you are given the coefficient of static friction and you have to find the applied force. But that's really a simpler problem than what we've got here. Hey, this is Mr. A, and I'd like to work a pretty tricky unbalanced forces problem. Pretty tricky for us. It's actually an example problem in the book where we had a crate, and there was an applied force on the crate of 100 newtons. So there was an applied force of 100 newtons. We had the force of gravity, of course, and we had normal force. And then there was a force of friction. It was a little bit smaller than the applied force. So there was going to be some net force that was acting on this box to accelerate it. And that's what the question wanted us to find. It wanted us to find what is the acceleration. Well, they also told us that the mass of the box is equal to 25 kilograms. And they told us that the coefficient of friction, kinetic friction, between the crate and the floor was 0.2. And that's all they told us, and they wanted us to find A. Looking at the free body diagram, there are some things that should jump out at us. The normal force and the force of gravity are in balance because the box isn't going up and down. So the force of gravity is equal to the normal force. And while we're at it, we can also say that the force of gravity is equal to the mass of the crate times the acceleration of gravity. So, given these two situations, we could say that the normal force, therefore, is equal to the mass of the crate times the acceleration of gravity. Some other relationships that we need to keep in mind, since this is a situation where we have kinetic friction, the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. Okay? None of these have the A that we're looking for. The A actually comes from Newton's law, which says that the net force on the object is going to cause the object to accelerate proportionally in accordance with its mass. Okay. So this F net is the net result of FA and FF. So F net is equal to, down here, F net is equal to FA minus FF. Now, I hope you can see that. This box is sitting on the floor. We're pushing on it with this force, and there's a force resisting us, but that resistance force isn't enough to overcome our force, so the box is moving, the box is accelerating. But not due to the original applied force, it's the net force of the applied force minus the friction force. Okay, hope that you can see that. Now I think we've got a complete picture, or at least all the pieces to the puzzle are laid out here. If we want to solve for acceleration, let me start working over here. Acceleration, then, if we divide both sides by the mass, is equal to F net divided by the mass. Oops, sorry, too many humps there. Okay, well, we know what the mass is, but we don't know what F net is. Well, we do know that F net is equal to FA minus FF. Okay, all over M. Okay, we know what FA is, but we don't know what FF is. But we do know that FF is mu Fn. So F A minus mu sub k, minus mu sub k F n all over M. Okay, now what is Fn? Goodness gracious. All right, we know that Fn is equal to mg, so it's F A minus mu sub k mg. Now I think that we have everything that we need to plug and play. FA is equal to 100 newtons. Mu sub k is equal to 0.2. Mass is equal to 25 kilograms. G is equal to 10. And mass is equal to 25 kilograms. I think that if you plug that all into your calculator, you will get 50 over 25, or the big number, 2 meters per second squared. Alright. So the approach to this problem was setting up the free body diagram, realizing that Fn and Fg were equal to each other, setting them equal to each other, writing down some of our premise equations for the kinetic force, friction, and some of these other relationships. Getting all the pieces of the puzzle laid out there so that when we go to solve for what we're looking for, we just keep substituting what we need. All right. Boy, that's messy, but this is what I expect you to be able to do. Hey, this is Mr. A, and I'd like to solve an unbalanced forces problem that I call sliding to a stop. And the sliding to a stop problem is actually a special case of an unbalanced forces problem in that we don't have any applied force. So imagine, if you will, a hockey puck or a shuffleboard on ice or on the concrete, and it has some initial velocity, but once it leaves the paddle, then it has a force of friction, which is causing the puck to slow down. There's a force of friction, but there's no force. The force that got it moving in the first place is long since gone, and now it's just coasting. If there was no friction, but there is friction, so it is decelerating. Now we still have the force of gravity acting on the puck, and we have the normal force acting on the puck, and that's good because we're gonna need those two in order to solve this problem. What ultimately we're looking for is what is the acceleration. What is the acceleration, or really the deceleration of the puck? So let's just put this over here for right now. When you're solving these problems, you need to do the free body diagram so that you can realize some of the relationships that are in play here. The normal force and the force of gravity are in balance, but the friction force is not in balance. The hockey puck is sliding horizontally. It's not bouncing up and down in this particular situation. So we can write that the normal force is equal to the force of gravity. And that's going to be really important when we try to find out the friction force. The friction force, and this is one of our standard equations that was given in the chapter. Here the puck is sliding, so it is mu sub k is the coefficient of kinetic friction times the normal force. Okay, so it's important to have these relationships in mind because, well, we're going to need them. We're given that the mass of the puck is equal to 0.2 kilograms, and that the coefficient of friction between the puck and the board, coefficient of kinetic friction, is equal to 0.33. Okay. So if we wanted to find out what this friction force is, I think we can do that fairly straightforward. So friction force, the force of friction on the puck, is equal to mu sub k times the normal force, but the normal force is equal to the force of gravity, right? So I can put, instead of F in here, I can put Fg, and that's good because we know that Fg, the force of gravity, is equal to mg. All right, so the friction force is equal to mu sub k times m times g. And we can actually plug some numbers in for that, right? So mu sub k is equal to 0.33, and the mass of the puck is equal to 0.2, and the force of gravity is equal to 10. Okay. So the friction force then is equal to 0.66 newtons. Okay. But we're not done yet, because what we're trying to find is the acceleration. So the acceleration, we can apply Newton's law that says that the force is proportional to the acceleration with respect to the mass, right? So F equals ma. So this is the friction force. We know the mass of the puck. Now we can find the acceleration. Just want to point out again, this friction force, that's the only thing that's acting on the puck. That is causing it to slow down. And it's going to slow down at a rate that's determined by the mass of the puck. So that if we wanted to determine the acceleration now, we have to solve for that. So acceleration is equal to the friction force divided by the mass, which is equal to 0.66 divided by 0.2. Okay, if I get my calculator, 0.66 divided by 0.2, 3.3. 3.3 what? 3.3 meters per second squared. We know that because we're using standard equations with variables with standard units. Okay. Now, there was a practice problem in which you had to take this one step farther, and knowing the deceleration, this is a deceleration, so you might want to put it a negative sign up here. Knowing the deceleration of the puck, I think the question number 24, practice problem number 24, was how far does that puck go? And that should be a skill that you have. Okay, but for this problem I just wanted to find that acceleration. I think once you find the acceleration, then I think you have to do a how fast was it going in order to determine your how far. But that's for another problem.